Okay, welcome back to our third chapter about elliptic differential operators. And we were talking last lecture mainly about the notion of a weak derivative, and in the end I introduced the Sobolev spaces, so spaces built above the L2 space of weakly differentiable functions that are together with their derivatives again in L2. So all L2 functions such that all derivatives up to order k in the weak sense are L2 functions. And this is a nice space because it turns out to be a Hilbert space with a scalar product that you get if you just add up all the L2 scalar products of the corresponding derivatives. And so this is, one has to show this is a scalar product, but this is not too complicated. But it's even nicer. The corresponding norm makes this space complete. So this is a Hilbert space, and we will even show that it is separable. So, and this was the theorem that I wrote on the blackboard in the end of the last lecture. And what still misses is the proof. So we have to do, still have to do two things. We have to show that this is, we have to show completeness. And then in the second step, we have to show separability. So let's start with completeness. So what do you do? Okay, we take a Cauchy sequence. Let uj be a Cauchy sequence in hk with respect to the corresponding norm. And then choose some multi-index that is that has length less than k, less or equal k. And then look at the differences of the corresponding derivatives, so d alpha uj minus d alpha uk for all j and k, the natural numbers. Okay, and this measured in L2. So this is finite because all these functions are in L2. But what is even more important, this term here is one of the summands in the corresponding HK norm. So the HK norm of this difference is bigger than this difference. So this is bounded from above by the difference of these two, by the difference of uj minus uk in the HK norm, because this is one of the addends you have there. So, and this means, as this is a Cauchy sequence into HK, for j and k large, this gets small, so this also gets small. So the sequence d alpha uj is a Cauchy sequence in L2. And now we are back to something which we know to be complete. So L2 is complete. So this sequence now converges for every multi-index with length less or equal alpha. So there is a limit. So we can set u alpha to be the limit j going to infinity d alpha uj in L2. This is an L2 limit. Okay. And what do we want? We want to show that this sequence is convergence in the HK. So we need a candidate for the limit. What is the candidate? Okay, the candidate is the function u whose derivatives this should be. So you just take the zero multi-index. So if you do this for the zero multi-index, you get uj minus uk in L2. And so uj itself is a Cauchy sequence in L2, and this has a limit. And this we call u. So u is the thing that you get for the zero multi-index. And now we have our candidate, and it remains to prove that the sequence converges to u. And surely we have to show that this u, which is a priori only in L2, is in HK. So we have to show that all derivatives of u up to order k, or weak derivatives, exist and are in L2. So we start with that. So take some multi-index that has length less than k, and take some test function phi in CC infinity of omega. And then we will see that u has weak derivatives, so we look at the scalar product of u with d alpha phi in L2. This scalar product, so uj converges to u in L2, so you can write this as the limit j going to infinity scalar product of uj with d alpha phi. Now, this, in fact, is an integral, uj times the complex conjugate of that one. So we are really at the definition of our weak derivatives. Weak derivatives just means by partial integration we can take the d alpha to the other side, getting some minus signs. So this is the limit j going to infinity minus 1 to the length of alpha d alpha uj, which is now okay because uj is an element of hk. Yeah. We know that uj is weakly differentiable. Phi. And now we can again take the limit in L2. Because we know what this does in L2. D alpha uj in L2 converges to u alpha. So this is u alpha phi with a minus 1 in front. Minus 1 u alpha phi. So at the moment we have a bunch of limits. Yeah, we have the u, and we have all these u alpha. For every multi-index we have another limit. But now it turns out these limits are fitting well together, because it turns out that the function u has a weak derivative of order alpha, and this weak derivative is exactly the limit u alpha of the alpha derivatives of uj. So this fits together well. So what we found is that if you take the function u defined as that to a weak derivative, this exists, and it is exactly the limit that you get if you take the weak derivatives of uj and take the limit. Okay, in particular, this is in L2. And this means that our function u is in hk, and that uj converges to u in hk, because every derivative of uj converges to the corresponding derivative of u, and then you can just plug these together in the norm. Okay, so we have completeness. Second thing, I claimed that this is always a separable space. So we have to prove separability. And the main thing also here, we will reduce that to the corresponding property of L2. So the L2 space on omega is a separable space, and we will reduce the separability of hk to L2. And this can be done with a easy trick, but as usual, if you get it, someone shows it to you, say, okay, this works, but to find it is the point. So what we consider is the following linear map going from hk to a Cartesian product of many copies of L2. So for every multi-index of length less than k, you take a copy of L2 and you make a Cartesian product out of them. Then this is a finite Cartesian product of separable Hilbert spaces, so this is a separable Hilbert space. And the map u just takes, the map phi just takes the function u and assigns it to the vector of all its weak derivatives up to order k. Just put them in a long vector. And then it turns out that this phi is not only a linear map, but it's an isometry. Because if you look what is the norm here. The norm is the sum of the, so it's the square root of the sums of the L2 norms of these things squared. And this is exactly what you also get here. So these two norms are the same. So it's an isometry. And now putting in that we already know that HK is a complete normed vector space with a scalar product, so it's a complete space. So if you take a complete space into an isometry, which is in particular bijective with an inverse that is also an isometry, what you get is that the image of HK is again a closed subspace in this product space. But this means that this image as a closed subspace of a separable Hilbert space is itself a separable Hilbert space. So this is separable. Yeah, but phi is an isometry, so HK also is separable. Okay, so in this way we can somehow inherit the separability of L2 to the HK spaces. Okay. I told you that these Sobolev spaces have some resemblance to the spaces of continuously differentiable functions in the sense that they are built on a base space, so L2, or the continuous functions, and they form a scale of functions whose derivatives again fall into the base space. Yeah? So you can think of HK, in some sense you can think of HK as the differentiable function in the L2 scale. A scale of differentiable function spaces in the L2 scale. But there is one thing that one has to keep in mind, which is sometimes forgotten, and then there are awful useless mistakes. So one warning. We know that every continuously differentiable function is weakly differentiable. So one might have the impression that if you have something that is CK, probably it should be HK. If you think of HK, as just k times weakly differentiable and CK as k times continuously differentiable, you could have this idea. And this is not a very good idea because this is false. And the point is that being in a Sobolev space is not only a quality of differentiability, but it contains, so this notion to be in a Sobolev space also contains some integrability. Yeah? U has to be in L2. It has to be square integrable. There are many functions that are nicely continuously differentiable, but not square integrable. And then they are not in HK. Yeah? So always keep in mind that being in a Sobolev space does say something about differentiability. Yeah? So up to the order k. This means there are weak derivatives up to some order, plus integrability. It does not only say there are a certain number of weak derivatives, but it also says all these derivatives are square integrable, are in L2. And this is an integrability thing, not a differentiability. Okay. So let's check some more properties of these Sobolev spaces. And when you have a new function space, a first thing to ask, or not the first, but one of the important things to ask always is, are there nice smaller function spaces that are dense? Yeah? Because if you want to do proofs, it's always nice to have a small dense subspace in which you can reduce things. So one question could be, what about CC infinity and HK? Yeah? So is CC infinity dense in HK? That's a question. And the answer is, as it is very often, that depends. And it depends on the domain that you, now, what I left out, CC infinity of what? And it turns out that, for instance, for the whole space, this is okay. And for all k, doesn't matter which k. But this is linked to the whole space, and you will see also in the proof. The proof that I will present will break down if you do not do the whole space. And we will also see later that as soon as you do not, as you have, for instance, a bounded set omega here, this will never be dense. So this depends on the domain that you have here, and this proposition is really linked to the whole space. So what do we have to do? We take a function u in hk, we take some Rn, we take some positive epsilon, and we have to find some CC infinity function that is less than epsilon away from u measured in the HK norm. Okay. And we will do this in 2 steps. So what are the problems that u is not itself in CC infinity? Okay, probably it's not smooth enough to be in CC infinity, and probably the support is too big. So we will address these issues step by step. So we will first look at the differentiability. So we will do some smoothing. That's the first step. Smooth this function out to make it C infinity. And what is the usual way to smooth functions out? You do a convolution with a nice modifier. So let's take a nice modifier, take some CC infinity function omega, as we already had several times, with support of theta in the unit ball, and such that the overall integral over Rn is 1. And then consider the corresponding modifier theta t. So again, theta t is the dilated and scaled version of theta. You do a convolution with u, and this I will call Vt. And then what do we get? What is this function Vt? First thing, this is a nicely differentiable thing, because we know if we have a convolution, we can put the derivative on whatever we want. And now I want to put it on the u, d alpha u. So for this is true whenever the length of alpha is less or equal k. And so this was Lemma 311 on Monday's lecture. And we know that this modified version approximates u. So if t goes to 0, this converges in L2 to u. So the alpha derivative of Vt minus the alpha derivative of u in L2 converges to 0 for t going to 0, and also for all alpha less or equal than k. Okay. So now this means that you can, that for every t positive, this thing is nicely differentiable, and so this function here is in CC infinity, in C infinity. That's the point. It's in C infinity. because theta t is arbitrarily often differentiable. And you can, and it's in HK. It's in HK because this derivative here, so this is in L2. Convoluting an L2 function with the modifier stays in L2. So this is in L2, meaning that Vt is in HK. Again, warning up there, C infinity does not give you HK in general. Think of a function continuously 5. It's nicely C infinity, but surely not square integrable. So this is an HK function, C infinity and HK, and all these derivatives go to 0, so tend to d alpha u. So if you take t0 small enough, you will get a C infinity function in HK that is arbitrarily close to d alpha u. And that was what we want to have for smoothing. So if you take some t0 small enough, we get that the difference of Vt0 to u measured in HK, so all those derivatives summed up, but not Rn, Rn, so that this is as small as you wish, and as we want to do it in 2 steps, so take it less than epsilon half. Okay, so now we have a smooth function that is close to u, and now we have to approximate this by something that is smooth and has compact support. So this is step 2, this is truncating. And okay, we cannot just truncate the function because this would again destroy the smoothness. So let's truncate a little bit more sophisticated way. So let's take some C infinity function eta such that eta of 0 is 1, and set now Wt to be eta of Tx Vt0 of x. Then this thing is C infinity, because that is C infinity and that is C infinity. It is even C infinity with a compact support because the epsilon is compactly, the eta is compactly supported. So if x is far enough out, this will be 0. So the product will be 0. So it's a C infinity function. As a C infinity function, it is also in HK, because a function that is continuous and compactly supported will be L2. And all the derivatives, all the classical derivatives, being the same as the weak derivatives, are also C infinity functions, so also in L2. So there's no problem. So this is a C infinity function in HK. And we have to now shrink the t. Now if you shrink the t, the support of eta gets wider and wider. And the hope is that we will get a convergence in HK. And this is what we still have to calculate. So for all multi-indices less than k, now we have to show that Wt, that every derivative of Wt in L2 goes to the corresponding derivative of u. So for t going to 0. So let's look at the alpha derivative of Wt. And this is now a little bit a nuisance because this is a general Leibniz rule. So you have to differentiate this product here. Okay, and let me single out the term where only the v is differentiated. This gives you eta of Tx times the alpha derivative of Vt0, and plus all the rest. So there is a bunch of more derivatives. So plus all the multi-indices that are less or equal than all the multi-indices beta that are less or equal than alpha, but strictly positive. So the beta equals 0 multi-index would be the one for this one. then you get the usual Leibniz rule, so beta over alpha, and then you have a beta derivative of this one, and the beta derivative of this one gives you a t to the modulus of beta, because at every derivative a t is coming out, times the beta derivative of eta, and you have an alpha minus beta derivative here, so d alpha minus beta vt0 of x. So this is the general Leibniz rule, what you get, and it's not of big importance how this looks like. What we now have to take care of is what happens if t goes to 0. No, because if we want to show that for t going to 0, this converges to vt0, to the alpha derivative of vt0. Okay, and this, and the convergence is in L2. And this works out fine because, this is the easy part here. All these functions here are some derivatives of C infinity functions with a compact support here. So all this is a bounded stuff here. There are some constants I do not want to bother about. This is bounded stuff. And if t goes to 0, this goes to 0. So all of this goes to 0. So it remains this first term here. And what happens here, if t goes to 0, the support of eta grows and grows. And this goes to eta of 0. So this is 1. This goes to 1. And now you have to make sure, so point-wise, this goes to d alpha vt0 at x. And now you only have to make sure that this is also true in the L2 sense, but this is just dominated convergence. So you have point-wise here, and this is, the whole function here can be dominated by some constant coming from eta times the function vt, d alpha vt0, which is in L2, and then you have a measure. So by dominated convergence, all of this stuff converges to d alpha vt0 of x in the L2 sense. Okay, and now choose your t close enough to 0 such that the difference here is again less or equal epsilon over 2. And then put the two together. So there exists a t1 such that wt1 minus vt1 measured in hk is less or equal epsilon over 2. And now you take the two together and you have found a function wt1 that is in CC infinity, and the distance in hk to u is less than epsilon. Okay. I want to write down one corollary that or one nice theorem about Sobolev functions that we can prove now. And I already told you the main benefit of this denseness of CC infinity is that you can do proofs by showing some equality only for CC infinity functions, and then make sure that both sides of the equation behave well under the limit in hk, and then you get the same equality for all hk functions. This is a usual thing that you do for proofs. And this is what I want to show here is one of these. And what this shows is that you can generalize the formula that we have for weak derivatives. So weak derivatives is this partial integration formula for all test functions in CC infinity. In fact, you have the same equality for all hk functions instead of CC infinity. So let k and n take two hk functions on the whole space, and then whenever you take a multi-index of length less than k, you get the formula of partial integration. So integral over Rn d alpha u times v is the same as -1 to the modulus of alpha times the integral over Rn u times d alpha v. So you have the formula of, if you saying this for all v in CC infinity is just the definition of the weak derivative. For all v in CC infinity, this is weak derivative of u. And what is new in this corollary is that the v can also be chosen in all of hk, and the equality stays valid. And the proof is now just the proof by density. As I said, if you take a v in CC infinity of Rn, this is just the definition of a weak derivative. And now, proposition 318 tells you that these functions are dense in hk. So what you have to check is that if vj goes to v in hk, then this integral with vk converges to this integral with v, but this is just some sort of scalar product in L2, and scalar products in L2 are continuous with respect to limits in L2, the same on this side. So both of these integrals will converge if vk goes to v in hk to the corresponding integrals with v, and so you get the equality. Okay. So we now have the spaces hk. We've seen the CC infinity functions are dense in there. And now it's time to slowly move towards why we introduce these spaces. So, okay, you can talk about these spaces, but the aim is to look at differential operators. In the end, to look at differential equations. To work on differential equations. And so these Sobolev spaces shall provide the functional analytic framework in which to look at partial differential equations. And if you have a partial differential equation, think of Poisson equation or Laplace equation, Laplace u equals 0 and some boundary thing, some f, or Laplace u equals f and u being 0 on the boundary, you always have boundary values. You have something on the boundary prescribed. And this is what we want to address next. So we want to somehow get such a Dirichlet condition, so the condition of a function being u on the boundary, we want to get this into the space. And this leads to the fourth subparagraph of this chapter, which is about the Sobolev space H10 of omega. And this will be the subspace of H1. So in a naive sense, so in an intuitive sense, this will be the subspace of H1, of the Sobolev space H1, of functions that are 0 on the boundary of omega. And this, if I say it like that, you will say, okay, this makes sense. Be aware this doesn't make sense. This doesn't make sense at all. If I have a domain omega, even in R2, and I look at H1 functions, then these are H1 functions are L2 functions that have a weak derivative that is in L2. And so this is an L2 function here, and I want to take about the values of this L2 function on the boundary. So first problem, the function is not defined on the boundary, but only in the interior of omega. Second problem, the function is an L2 function. It's a class of it's an equivalence class of functions that are the same almost everywhere. The boundary is a null set. So prescribing values on a null set for an L2 function is nonsense. So this is not an easy task. Yeah? But nevertheless, we will succeed in having some notion of being 0 on the boundary for Sobolev functions. And this is one of the nice features of Sobolev's function, that it is possible to define a notion of being 0 on the boundary, even if this is a null set. And this somehow makes these spaces worth to work with them in context with boundary value problems. If you have a boundary value problem, you have to talk about boundary values. This is a tautology, but important in this context. Okay, so the aim is give a meaning to some Dirichlet boundary condition. So a Dirichlet boundary condition is the easiest boundary condition that usually runs around when you do partial differential equations. So it just means you want to prescribe that your function omega is 0 on the boundary of, that your function u is 0 on the boundary of omega. This is what we want to talk about. And as I told you, this is not trivial. There is one case where this works, and this is the one-dimensional case. Because we saw in the last lecture that every function in H1 of R in one dimension has a continuous representative, and this representative continues up to the boundary. And for this continuous representative, you have boundary values, and you can decide if they are 0 or not. So there, everything is okay. So if you have a u in H1 of some open interval AB, then, okay, what we saw in the last lecture was that if you have a function u that is L1 with a weak derivative in L1, then you have a continuous representative. Okay, we are in H1, this is L2, so L1, L2, let's see. But it works. If u is in H1, then u and u prime are in L2 of AB. AB is a finite measure space. And for finite measure spaces, L2 is embedded into L1. So this means that if you have a function u in H1 of an interval, of a bounded interval, then u and u prime are both in L1. So the function u is absolutely continuous or has a continuous representative. And so this was Corollary 314. We can do the following definition. So the Corollary 314 tells you that this u has a continuous representative continuous on the closed interval AB. So we can talk about the boundary values. So if you have a bounded interval in R, then you can define the so-called trace operator. Trace going from H1 of AB to C2 and assigning to u the boundary values. So u tilde was this continuous representative, u tilde of A, u tilde of B. Because for the continuous representative, these two numbers make sense. And then this trace operator turns out to be a bounded linear operator. And that it is linear, I hope you will accept immediately. It's just plugging in numbers into a function. So this is a linear thing. Why is it bounded? Because you can control the norm of this, or the absolute value. This is the norm here is absolute value. You can control the absolute value of these two numbers by the H1 norm using the fundamental theorem of calculus. Well, we've seen that by the last lecture. We've seen that you can control the supremum norm of u tilde by what was it? It was 1 over b minus a times the L1 norm of u prime, of u, plus the L1 norm of u prime, something like that. Yeah? And these can be controlled by the L2 norms, and the sum of the L2 norms is controlled by the H1 norm. So this is controlled by the H1 norm, so the supremum here is controlled by the H1 norm, so you can control these two. So it's really a bounded linear operator from H1 to C2. And now it's worthwhile to check the following thing. And this is one of the exercises that we propose for this week. In 1D, so if you have an H1 function on a bounded interval, then you have the following equivalence. You have that let's say U is in the kernel of the trace operator. So U has zero boundary conditions. Kernel of the trace operator is the functions that are mapped to 0, so with U tilde of A and U tilde of B being 0. U is in the kernel of the trace operator if and only if U is in the H1 closure of CC infinity. So if you have a function that can be approximated in the H1 norm by CC infinity functions, then this has zero boundary values. And the other way around, if a function has zero boundary values, then it's in the H1 closure of CC infinity. So we've seen up there you can approximate every HK function on RD, so every H1 function on RD by CC infinity function on RD in the H1 norm. You already see here on the bounded interval this will not work, because every function that can be approximated by CC infinity functions in the H1 norm has a zero trace, so has zero boundary values, which somehow seems the right thing. If you approximate by CC infinity functions, all these functions are zero at the boundary, and this will not change by approximating. But that does mean that this CC infinity in general will not be dense in the whole of H1, because the function constantly 5 is in H1 of the interval. This is a bounded interval. The function 5 is nicely L2. Its derivative 0 is also an L2, which works. But it cannot be approximated here. Okay, this is the one thing that is interesting. Okay, I already told you the proof is one of the exercises. And the other interesting thing here, or the other thing why this theorem is now interesting for our course, is this gives us the motivation of how to define zero boundary values in arbitrary dimensions and in arbitrary open sets omega by just taking this as a definition. Now this is now, in some sense, this is cheating, because, no, not cheating, but it's not very satisfactory. We want to define boundary values of our functions. You cannot is wrong. But it's really sophisticated, complicated problem for a general boundary. If you just have an open set omega and you want to define traces on the boundary, this is impossible. And it's a really hard problem in potential analysis, or if you look at it the other way around, in geometric measure theory, to characterize the sort of domains for which, in some sense, you can define traces on the boundary. This is a hard problem. And we just circumvent all these problems by defining being zero on the boundary means being in the H1 closure of CC infinity. We just define it like that. And this is the next definition. So this is definition 322. Now we are again in Rn. Omega is just an open subset of Rn, and we now define H10 of omega. So intuitively the set of, or the space of all h1 functions on omega that vanish on the boundary, whatever that means. And we define it by saying, okay, take the CC infinity functions, close them up in the norm of h1, and what you get is some closed subspace of h1, obviously. Closure of something is a closed subspace. It's some closed subspace of h1. For omega equal Rn, this closed subspace will be all of h1. That is what we proved up there. And for omega different from Rn, we do not know. But it's some closed subspace. And intuitively, you should think of this closed subspace as the set of all h1 functions that vanish on the boundary of omega. Okay. We will come back a little bit to this later. So in lecture 10, we will show you that if you take omega to be Rn without the origin, so you just take out the tiny origin, then you still have that h10 and h1 coincide. So in some sense, for dimension greater than 2, obviously, greater than equal than 2. In dimension 1, this doesn't work, but in dimension up, starting at 2, if you just take out the origin, in some sense, the Sobolev norm will not notice. So only the origin is not enough of a boundary for the Sobolev space to be seen. In this case, also, CC infinity is dense in H1. But I will show you now a result that tells you that if you take out more, so if you have, so it gives you a huge class of domains that are not the whole space in which the space H10 is a proper closed subspace of H1. And this is the following lemma. So this tells you whenever you take out something that has a positive measure, so if the complement of omega in Rn has positive Lebesgue measure, then you have the result that if gradient is and you have u in H10, then you get the following thing: whenever the gradient of u is 0, then u is 0. And what that does mean is, in particular, if you have an omega that has a bounded Lebesgue measure, so either a bounded omega or an unbounded omega that still has finite measure, then H10 is a proper subspace of H1. Because on a bounded subset, H1 contains constants non-zero. On a space with finite measure, the constant functions are nice H1 functions. Because on a space with finite measure, constants are L2 and the derivatives are 0, so they're also an L2. This works. But this tells you if you have a constant function, it must be the 0 function. So in this space, the only constant function is the 0 function. So, and this is also one of the exercises we proposed this week. Also to make you accustomed with these Sobolev space things. Okay. Okay, there's one more thing to say about Sobolev spaces before we start to get into somehow the main aim of this section of this chapter to elliptic differential operators, and this is the so-called Poincaré inequality, and this I will do after the break. So let's first take some rest. Okay, let's start the second part of this lecture, and I already told you we will prove an important inequality, the so-called Poincaré inequality, and I need one more geometric notion, so some condition on the domain omega that has to be fulfilled for this inequality to hold. And this is, we say that an omega in Rn is contained in a strip, and this is a very talking name of the definition. This is exactly what it means. So it's contained in a strip of height h. If there is some coordinate direction, so some j between 1 and n, and there is a number a in R, such that for all x in omega, the jth component of x is bounded, so is in A plus H. So this just means, so if you do it in 2 dimension, this means there is some strip in which the domain lies. So the domain must, you can also see it in this way, the domain is contained in a strip if there is one coordinate direction in which the domain is bounded. Okay, so it need not be bounded as a whole, but it has to be bounded in one coordinate direction. And now I can formulate the inequality, so-called Poincaré inequality, which is a feature that all functions in H1 0, so in our space of H1 functions with 0 boundary values have, at least if omega is contained in a strip. So if omega is contained in a strip of height h, then for all u in H1 0 of omega, so the H1 functions that can be approximated by CC infinity functions in omega, you get the following estimate. So the L2 norm of u can be controlled by the L2 norm of the derivative of u. And there is a constant in front, and this is h over square root of 2. Note, this inequality can never ever hold in H1 without the 0, at least if omega is a bounded set. Because if omega is a bounded set, as before, H1 contains non-zero constant functions. For a non-zero constant functions, this is 0, but this is not. So this is intimately linked to the 0 here. Okay. So let's give the proof. And this is a rather important inequality you will find, perhaps you've seen already. It appears in many places and will also play an important role in our lectures because it allows to control the L2 norm of u by having some control on the gradient. Okay. First thing, let's use that this is the closure of CC infinity and reduce to CC infinity functions. So we will only prove the inequality for CC infinity functions u, and then again it's a density thing. Yeah? Both these left and right hand side expression are continuous in the H1. So if you have convergence in H1, and so once you have proved this inequality for CC infinity functions, you get it immediately on H1 0 by density. So then density. And here the density of CC infinity in H1 0 is just by definition. This is the closure of that one. And then one more or some more reductions. Without loss of generality, you can shift the whole domain such that, and turn the whole domain such that the strip is in direction of the first coordinate, and the A is 0. So without loss of generality, I will take J equals 1 and A equals 0 in the definition of being in a strip. This is just by rotating and shifting your domain. And rotating and shifting the domain doesn't change anything here. Rotating and shifting doesn't change L2 norms. Okay. So what we know is that our domain is such that x1 is between 0 and h for all x in omega. So this is the shifted and rotated version of being in a strip. Okay. And then as a notation, whenever I have an x in Rn, now the first component is something special, so I will take this out and the rest I will denote by x prime. Okay. And finally, we extend u by 0 outside of omega. Because what I will write down are integrals that are over the whole strip. Yeah? So now without loss of generality thing, here is now the one axis, there is the other, here's the strip. So this is h. And the omega is somewhere here inside. Yeah? Might be unbounded. Yeah? And I will do integrals going over the whole strip, of parts of the whole strip, and out of omega, formally u is not defined. That's why please think of u being 0 outside. Okay. And then we can start to estimate u of x1 x prime squared. And now u, as I said, is CC infinity. So I can apply the fundamental theorem of calculus in the one variable x1. So I can rewrite this as the integral going from 0 to x1 d1u of s x prime ds squared. It's more easily seen from here to here. Yeah? This is integral over derivative, so this is u at x1 x prime minus u at 0 and x prime. But u at 0 and x prime is on the boundary of the strip, so either it's outside of omega, or if omega really touches here, it's at the boundary of omega, but we have a CC infinity function in omega, so it's 0 here. Okay. Now use the Cauchy-Schwarz inequality. So this is a scalar product of 1 with this derivative. So if you do the Cauchy-Schwarz inequality, you get x1 times the integral from 0 to h, from 0 to x1, d1u of s x prime ds and the square and the modulus in here. And then I estimate further by integrating up to h, because I integrate something positive. So if I integrate a longer distance, this is more. Okay. And now, why did I do this? Because this has, I want to calculate this one, not this one. So what I want to calculate is the L2 norm of omega, but we will see in a minute how this helps. So let's write down the L2 norm and take out the x1, the x1 dependence. So this is u of x1 x prime squared dx1 x prime with the squared here. I only write the square, not to write so many square roots. So this is exactly what we have here. So let's take this estimate in there. So this gives you an integral over omega, the x1. Then there's an integral going from 0 to h over the modulus of d1u s x prime squared, ds. And then the x1 x prime. So in some sense there is now too many integrals, yeah? But this will sort out in a minute. this is all positive, so you can swap the integrals. Doing some Tonelli. This gives you an integral over 0 to h over x1 dx1. This is... Yeah, and then you are left with an integral over omega d1u of sx prime modulus squared dx ds dx prime. Okay, this is not too complicated to calculate. Integral from 0 to h over x1 dx1. This is a half h squared. And this is the square root, is the L2 norm of the first partial derivative of u. But this can be estimated by the L2 norm of the gradient. Well, this is a root estimate, but it works. So take all the other partial derivatives and add them up. And now you have what you want. So taking the square root, you get the L2 norm of u. So that's all equal h over square root of 2 times the L2 norm of the gradient of u. Okay. So this is the Poincare inequality, which we will meet later in the course. And you will surely meet in several other courses as well. Okay, so now let's come to the heart of the thing, and let's define our elliptic operators, our elliptic differential operators. And in some sense, in this fifth section, the elliptic differential operators in divergence forms, in this fifth subchapter, the preparations that we did in subchapters 1 to 4 of this week and that we did in last week about sesquilinear forms now come all together. So what we will do now, what is the aim, is to define things like the Laplace operator and more general differential operators, but think of the Laplace as the model case, to define these operators as closed and nice operators in L2, as unbounded operators in L2, using our framework of sesquilinear forms. That's why we did this last week. And I will not only consider the Laplace operator, but take a more general class of operators. You can think of the Laplace. The Laplace operator is the divergence of the gradient. So Laplace u is divergence of gradient u. Gradient u gives you a vector. Divergence makes from the vector again a scalar. But here you have a vector, so you can even put in some matrix here. And this is what is called a divergence form operator. So it's a second order differential operator. If you take A to be the identity map, you get the Laplacian. But for other matrices here, you get other operators. And when you come from physics in these, or from mechanics in these coefficients in this matrix A, usually there's all the information about the material that you're looking at. So this A could, for instance, be heat capacity or diffusivity or whatever. Okay, so that's the sort of operators that we will look at. So we have this matrix A, and this matrix A can even be dependent on the point of the point x in omega. So at every point in omega, we will have another matrix. So we say that A is a function going from omega to the linear maps on Cn, so the n by n matrices. And we want, okay, it has to be measurable, otherwise we get in big trouble. And we will only here consider the case where it is bounded. So a bounded function from omega to the n by n matrices, measurable and bounded. And throughout all this section, this will be, A will mean this function, so this matrix valued function. And with capital lambda, we will abbreviate the essential supremum of this map. So the essential supremum for x and omega, A of x, measured by some matrix norm. And this is a finite thing because we wanted the function to be of L infinity. Okay, and now we consider the corresponding elliptic partial differential equation to this differential operator. So we look at minus divergence of A gradient U equals F with Dirichlet boundary conditions. So this should be fulfilled in omega and boundary condition 0. So we search for functions that are 0 on the boundary and fulfill this second order partial differential equation in omega. And again, if A is the identity matrix, this is the Laplace operator, then what we have here is the classical Poisson problem. Poisson equation, finding functions with 0 boundary values such that Laplace U is a given function f. And the aim is now to reformulate this partial differential equation in an L2 framework using our form approach of the last lecture. So what do we need for the form approach? We need a Hilbert space. In fact, we need two Hilbert spaces. We need one large Hilbert space where the operator lives in as an unbounded operator, and we need a smaller Hilbert space which is the domain of the form, the sesquilinear form. It is a nice coincidence we have two Hilbert spaces, smaller and the larger one. So in the notation of chapter 2, we consider the case where H is L2 of omega. V, so the form domain, is H10 of omega. We take H10 because then we have incorporated this boundary condition here already in the space. So we are looking for solutions in H10, and this gives us the boundary condition for free. And this is exactly the situation we had in lecture 2. We have a big Hilbert space. H10 is also a Hilbert space because it's a closed subspace of a Hilbert space. It's a closed subspace of H1. H1 is a Hilbert space. Closed subspaces of Hilbert spaces are Hilbert spaces. So this is a Hilbert space, and it's a Hilbert space that is contained in L2. It's exactly the situation, and continuously included in L2. It's exactly the situation we had in the last lecture, in the last week. And then there is this space V prime that we need. So the dual of V, the antidual of V, and in this context, this is often denoted by H minus 1 of omega, because this is in some sense minus 1 differentiable function. Be cautious, but this is a usual notation for this antidual of H10. Okay, and now how do we define the form? I claim that if you do the following thing, you do the right thing. So we have to define a form, a sesquilinear form, H10 times H10 to the complex numbers. And we take the following: AUV is the integral over omega A times gradient U gradient V bar. Convince yourself this is a nicely defined form on H10. For H10, there is one derivative in L2, so this is an L2 function, this is an L2 function, this is an L infinity function, so this is L2, L2 infinity, this is a nice, by Cauchy-Schwarz and Pölder, this is a nicely finite integral. For every U and V in H10, this will give you a complex number. This is sesquilinear, it's linear in the first component and linear in the second. It's a nice thing. It's even a bounded form. So now we can go through all the properties of sesquilinear forms that we had in the last lecture, in the last week. So first I claim this form is bounded. What do we have to do? We have to look at A of uv, and we have to bound it by the norms of u and v. But that is what I just told you. This is, this is integral over omega A gradient u gradient v bar. But in modulus, now you take them, you can do it in whatever. So this is L2, this is L2, this is L infinity, so this is L2. So you can, by some Cauchy-Schwarz, you can bound this by A gradient u in L2 times gradient v in L2. Now this is L infinity, this is L2, this is less than the L infinity bound of A, this is lambda, times the L2 norm of the gradient, times the L2 norm of the gradient of V. This is not exactly what we want to have, because for boundedness we have to bound this by U and V in the norm of the Hilbert space V, so in the H1 norm. Okay, but this is part of the H1 norm. The H1 norm is this squared plus the L2 norm of U squared and the square root. So you can just make this bigger by estimating this with the H1 norm of U times the H1 norm of V. Okay, and this now is boundedness of the form. And once we have a bounded form, so this is for all uv in H10 of omega. Once you have a bounded form, the theorems or remarks 214 and 216 now give us two operators. This was the main thing about last week. Once you have a bounded sesquilinear form, you get for free two operators. One bounded going from V to V prime. But this was denoted by this calligraphic L. So it's a bounded operator going from V to V prime. And one unbounded operator in L2. This was notated by the Roman L. So these are the two operators associated to A on V or in H respectively. And what do we know? We know that this operator LU equals F. This is now the result of lecture 2. If and only if F is in the Hilbert space H, so in L2 of omega. U is in the Hilbert space V, so in H10 of omega. And you have the equality that A of uv, so A gradient u gradient v bar, is the same as integral over omega fv bar for all v in H10 of omega. This was the defining thing of these operators. So what we find here is not exactly our differential equation, but it's what is called the weak formulation of this differential equation. If all the functions here are nice, so if A gradient u if A gradient u is weakly differentiable, this is a great if. In general, it will not be, because the A is just a bounded measurable function. So the A could be really nasty. So in general, it's not. But suppose A gradient u is a weakly differentiable function, then you can do the partial integration. You can put this gradient over here. This will give you a minus divergence. So if this is a weakly differentiable function, then you get minus divergence A gradient u v equals integral fv for all v. Fundamental theorem of calculus of variations minus divergence A gradient u equals f. So if you have this and the functions are nicely behaved, then u is a solution to the problem up there, or seen other way around. Once you have a solution of the problem up there, it will be a solution of this one. So this is a weaker formulation. But nevertheless, so in some weak sense, we can say every U that fulfills this one will be a solution in some weak sense of the problem of that. Okay. And now, if you look again into the last week's lecture, we had these two operators, calligraphic L and L, and then we started to see that if the form has some nice properties, ellipticity, accretivity, and all this stuff, then the operator L also gets nice properties, sectoriality, and M accretivity, all these things. And this is now the next thing to check. This sort of forms, is it nice enough to apply all the rest of this lecture to? And as you will already assume yes, because otherwise we wouldn't have done all these parts in lecture 2. So it turns out that at least if we have to restrict our operator matrices A a little bit. Because if we want to go in direction of elliptic problems, and it's also in the headline, we want to look at elliptic operators, then what does elliptic, in some intuitive way, elliptic means that something must be positive. So AUU must be, the form applied twice to the same thing must be something positive. So for this to come out here, what you need is some sort of positive definiteness of the matrix A. So you need that A gradient U gets something positive. And this is what we will call elliptic. So we say that the matrix function A is elliptic if there exists some positive lambda. So this is now small lambda, such that for almost all x in omega and for all psi in Cn, we have the following estimate. If you look at A of x, so f x is a matrix multiplied with a vector, psi is a vector. So this can be multiplied again with psi. This is now a complex number. And if you look at the real part of this complex number, we want that to be positive and bounded uniformly in x by lambda times the modulus of psi squared. You can see this as some sort of uniform positive definiteness of the matrix A. It's not really because you have this real part and stuff, but so you need this estimate for the quadratic form given by A of x. This is what is written here, the quadratic form given by A of x. And this quadratic form in real part must be uniformly in x bounded from below by the square of by some constant times the square of modulus of x. Okay, and whenever you have a matrix like that, we call that an elliptic matrix. Example, identity. The Laplace operator, the most important elliptic operator in divergence form. If this is constantly the identity, then this is then you can take lambda equals 1 and everything works out fine. Like this, for this matrix valued function A, there are now two very important characterizing numbers. The capital lambda, yes? Yeah, there's a bar missing. There, you're right. Sure. This must be or I have to write a scalar product. Bar, or you take a scalar product. Okay, so we have now two characterizing numbers for this function A. We have the capital lambda, which is the L infinity bound, and we have the small lambda, which is the ellipticity constant. And they are both important. They appear again and again. And Usually, capital lambda is a rather large thing. This is the infinity bound, and this is a rather small thing. Yeah? But it must be strictly positive. Otherwise, all the theory that we will develop now breaks down. Okay. So, but if we have such an elliptic matrix, then the corresponding differential operator L minus divergence A gradient, dot, here's the function that you plug in, is called an elliptic operator in divergence form. So that's the guys that are referred to in the headline. And we do it here in H10, so with Dirichlet boundary conditions. Okay. And the most important special case is take A to be constantly the identity matrix. In this case, you get the Laplace operator. Yeah. So we will then write minus Laplace in, or to get minus the Laplace operator, and we will call this minus Laplace with index H10 to indicate that as a form domain we took H10, so we have Dirichlet boundary condition, and this is the negative Dirichlet Laplace. You can now ask the question, why always this minus sign? Huh? So we have, why is L minus divergence A gradient? L is minus divergence A gradient in order to have the form A, the small a without the minus sign. So this minus sign appears somewhere. You cannot avoid it. At some point you have a minus sign because between the operator A, so between the operator divergence A gradient and the form, there is a partial integration. One partial integration gives you a minus sign. So you have to put the minus sign somewhere, either there or there. The choice to put it on this side or on the other side will then, in all our later considerations, flip everything around. Yeah? So when you put the minus sign like this, you have the spectrum on your operator on the positive real line. If you put it the other way, you have negative on the positive half space, half plane of the complex plane. If you put it on the other side, all these flips. You have to make a choice. We have this choice, and we will stay with this all the time. But somewhere you have this minus sign. Okay. Okay, and now let's check all these ellipticity and sectoriality things. And the nice thing that we find is when you start with an elliptic matrix function, and this is the only thing you need, so measurable, bounded, elliptic. If you start with any of these functions, you always get a really, really nice sesquilinear form. You already saw it's always bounded, but it's not only bounded, it is elliptic, and it is sectorial. So all the stuff we did in chapter 2 comes back, and you can even give a first root estimate of this angle. The angle of sectoriality is at least the arctangent of the quotient of the two characterizing numbers of the matrix. So you take the capital lambda divided by the small lambda. The arctangent of this ratio is at least the angle of sectoriality. Perhaps it's more. It is more in general, but this is the first root estimate that we get. So some proof that it is bounded we already saw. Huh? This is something somewhere over there on the blackboard. Second thing, it's elliptic. So again, what does elliptic mean? Elliptic means that whenever you take a function in the form domain, so in our case in H10 of omega, it must be possible to to estimate the real part of the quadratic form from below by some number times no, there must be some lambda or some constant. I think it was called omega. So what we need is that the real part plus some omega times UU scalar product in L2 can be estimated from below by some constant times the H10 norm squared. Yeah? So this was ellipticity. And it would be a bad choice of notation if an elliptic matrix function wouldn't give an elliptic form. So it's elliptic. And it's not that difficult to see. So what about the real part of AU of the quadratic form? This is writing out the form. The real part of A of x gradient u of x bar dx. Now this gives you just the modulus of gradient of u. And so first thing, the real part of A times psi bar, this is exactly what we have here. So by ellipticity of A, so this is ellipticity of A, we can estimate the integrand by small lambda times gradient of u squared dx. Okay, and this is now lambda times the L2 norm squared of the gradient. And if now on both sides of this inequality you add lambda times the L2 norm of omega, L2 norm of u, here you get the square of the H1 norm, and here you get that. So this means real part of A of u plus lambda times u L2 omega squared is greater or equal than lambda times u in H1 0 of omega squared, and this is exactly ellipticity. Okay. So, third thing, we have to make sure that our form is sectorial. And there we use something that we had in the last lecture. This was 226. This was a short lemma that told you if you can estimate the real part of the quadratic, the imaginary part of the quadratic form by the real part, then you immediately get sectoriality. And this is very easy here. So the imaginary part of this quadratic form, okay, this is always bounded by the modulus of the quadratic form, just because the imaginary part is always less than the absolute value. And now this is just boundedness of A. So this is bounded by capital lambda times the gradient u in L2. So this was the calculation that we did here. So A of UU can be bounded by capital lambda gradient u L2, gradient u L2, gradient u squared. And now you use ellipticity. The gradient of u in L2 can be estimated from above by the real part of AU divided by small lambda. So this is part 2. This is capital lambda divided by small lambda, real part of A of u. And this was exactly, now it's 226 now gives the claim. 226 told you that whenever you have a form where the imaginary part of the quadratic form can be estimated by some constant times the real part, then this is a sectorial form, and the arc tangent of this constant is the angle is at least the arc tangent of this constant. This was 226. In fact, as I already told you, this angle can be made better. For more details, see exercise 3.6. And I want to end all this discussion. Let me somehow summarize everything in Theorem 329. So once you have an elliptic coefficient matrix A, we can look at the corresponding divergence form operator. So if this is elliptic, so if the matrix function is elliptic, then we have the following properties. And now this is more or less harvesting what we did in lecture 2. Because now we know that our form A is nice, it's elliptic, it's bounded, it's sectorial of some angle, so we can take all the information and find things about L. So now we know that, for instance, L is also sectorial. And the sectoriality angle of L is the sectoriality angle of the form. This is arctangent of something, so it's surely strictly less than pi over 2. For every choice of lambda and lambda, you always have a sectorial operator of an angle less than 2, pi over 2. We get that L is injective. We get that we also know something about the adjoint of L. This you have to look a little bit on these forms that we consider here. So this form written over there, A times gradient U gradient V bar. If you do an adjoint, so the adjoint form is A of VU bar. And if you do the calculation, you will find that is exactly the form that corresponds to the same thing with the adjoint of A instead of A. So the adjoint goes onto the A. So L star is the same as the divergence form operators, where you have here. So this star is now a star in Cn times n, so in the n by n matrices. This is just the Hermitian matrix. So transposed and complex conjugated. So L star is of the same quality as L. This immediately also implies that L is self-adjoint if and only if A is Hermitian almost everywhere, so if A and A star coincide almost everywhere. And last thing, and this is where the Poincaré inequality comes into play, you can even have a criterion, a sufficient criterion for L being invertible. L is invertible if omega is contained in a strip. So if you can apply the Poincaré inequality. Okay, so there is now missing 2 or 3 lines of proofs. So B and D is from the very beginning intended to be an exercise, so this is okay. A is just citing the right numbers in week 2, because there we saw whenever you have a sectorial sesquilinear form, the corresponding operator is always also sectorial, at least at the same angle, so this is okay. And this is a small calculation that you find in the lecture notes, just showing that, as I told you, that this star goes over to the matrix star in the m by n matrices. Okay, so now we have our the main actor for the next remaining 11 weeks of internet seminar will be these operators. So these operators L in divergence form for various choices of matrices A. And what we achieved now is that we have a clear definition of these operators, and we already know many of their features. So they are really nice operators in L2, sectorial, injective. We know something about their adjoints. We know when they are self-adjoint. So we have a good starting point to further investigate these operators, and this will then be the topic of the forthcoming weeks. So this is all for today and for this week. Thank you for listening, and see you again on Monday.